So chapter 13 is all about gravitation. Gravitation is one of those weird things where we know the most about it because it's one of the first fundamental forces that we actually encountered and analyzed, but only up until recently we didn't really understand how gravity worked. There were lots of experiments on it, lots of different theories, but in reality, only in the past few years did we really come to an understanding of what gravity is. When you guys get back from however long a period we're away, I'll go into more detail on that. But all you really need to know is that gravitation tells us that all matter in the universe attracts all other matter. You already know this. We've talked about Earth's gravitational pull on us. Now we're analyzing the gravitational pull between individual objects that have mass. So, for example, if we have mass 1, and we have mass 2, and they are separated by some distance r. So mass 1, mass 2, they're separated by some distance r. We know that the force of gravity between these two objects is given by the following equation. The force of gravity between the two objects is equal to big G, I'll come back to that in a second, m1, m2 over r squared. That is our gravitational force equation. Big G, m1, m2 over r squared. Big G is a constant. It is known as the gravitational constant, not to be confused with the little g that we used for Earth, 9.8 meters per second squared. Big G is really a nasty thing that you'll come to memorize with a little bit of time because you're going to use it so often in these problems. Big G is 6.67 times 10 to the minus 11, and then I got to check the units here, Newton meter squared per kilogram squared, okay? 6.67 times 10 to the minus 11. It's got a Newton inside there. The meter squared is going to cancel out with the meter squared on the r squared term, and the kilogram squared in the denominator is going to kill the kilogram squared up in the mass term, okay? Both of these objects will feel the exact same force of gravity. You have to ask yourself why, and if we were in class, I would pause and I would ask you guys to explain to me why these two masses feel the same force of gravity between each other. The reason why, dramatic pause, is Newton's third law, action-reaction. So M2 is pulled by M1, and M1 is pulled by M2. And the force of gravity between those two objects is the same. We've talked about this before when we've talked about Earth's gravitational pull on us. The Earth pulls down on us, we pull up on the Earth. However, we don't talk about the acceleration of the Earth because the Earth has such a big mass. Okay? So when it comes time to calculate these, it's pretty straightforward. It's not really that big a deal. If we have two masses, let's say we have on some kind of x-axis, we have a 0.2 kilogram mass, 0.2 kilograms. This guy over here is 0.5 kilograms, and the distance between the two masses is 0.5 meters, okay? If we want to calculate the force of gravity between those two guys, we would do the force of gravity is equal to big G, m1, m2 over r squared, 6.67 times 10 to the minus 11, multiplied by, be careful on these masses, they need to be in kilograms, so please be careful on that. This is going to be 0.2 kilograms, 0.5 kilograms, divided by the distance between the two masses. Make sure that your distance is in meters, 0.5, the quantity squared, and we get a force of gravity for these two masses is going to be 2.66 times 10 to the minus 11 newtons. Now you have to ask yourself, is that a really, really big force or is that a really, really small force? And the answer is, because this times 10 to the minus 11, that's a really, really small amount of force, okay? So these two masses, because the masses themselves are very small, when we've talked about masses before, we've used the mass of the Earth, which is really freaking big. Because these two masses are so small, and because this G constant is really, really small, 6.67 times 10 to the minus 11, the force of gravity between those two masses is very, very small. Okay? Now what happens if we have more than two masses? Well, thankfully, all we have to do is add up the force of gravity on the individual mass from any other masses. Okay, so here's another example. Hopefully I can fit this whole thing right here. Okay, we've got another x-axis. We've got a 1 kilogram mass, and then a 2 kilogram mass. And then over here, we've got a 0.5 kilogram mass. The distance between the 1 and the 2, the 1 kilogram and the 2 kilogram, is going to be 1 meter. And then the distance between the 2 and the 0.5 is going to be 1.5 meters. Okay? Now in this problem, we want to find the net force on the 2 kilogram mass. The net force on the 2 kilogram mass. In order to find that, we need to figure out the force of gravity from the other two masses. Okay? So I'm going to get innovative here a little bit. Hopefully the red shows up. Okay? The 1 kilogram mass is going to pull the 2 kilogram mass right or left. Dramatic pause. It's going to pull the 2 kilogram mass to the left. So the 2 kilogram mass is going to feel a force to the left from the 1 kilogram mass. The 0.5 kilogram mass is going to pull the 2 kilogram mass, dramatic pause, to the right. Okay? So we've got forces in opposite directions. The 1 kilogram mass is going to try to pull us to the left. The 0.5 kilogram mass is going to pull us to the right. So are we going to add those forces or are we going to subtract them? Correct answer is we're going to subtract them. I would keep the 0.5 kilogram mass positive, the 0.5 kilogram mass the positive direction, and I would keep the 1 kilogram mass the negative direction. Okay? So the net force, and again, we're trying to find the net force on the 2 kilogram mass, is going to be 6.67 times 10 to the minus 11 multiplied by, let's use the 2 kilogram mass, the 0.5 kilogram mass, divided by the radius. The radius between these two guys is 1.5, the quantity squared. We're going to subtract the force of gravity from the 1 kilogram mass because that's going to pull us to the left. So minus 6.67 times 10 to the minus 11 multiplied by 1 multiplied by 2 divided by the distance, which is 1 meter, the quantity squared. Okay? And we should get a net force. I apologize that this went so low on here, but we're only using one whiteboard for the camera. This net force is going to be negative 1.04 times 10 to the minus 10 newtons. The minus sign tells us that overall this 2 kilogram mass is being pulled to the left. Now that should make sense. The distance between these two guys is smaller. Notice that the distance is a factor here in the force of gravity equation. The mass of these two guys is bigger, so we expect this force of gravity to be bigger for those two reasons. So if you want to talk about which force wins, or which force is going to determine the overall direction of the force on the 2 kilogram mass, it's going to be the 1 kilogram. That's why there's a minus sign there. Okay? Fairly straightforward. These calculations aren't too hard. It's something to consider. You want to get a little bit of practice with them.